Hello, hello, and welcome back to my restless late night exploration of recurring tutoring worksheet number 8. Now that we've done the first mechanical part here, we're going to go on to parts B and C of this. So in part B, basically all we're doing is we are taking the B tree we just created. So not this one, this is the one before we inserted everything. We're taking this one, and we're going to turn it into its corresponding red-black tree. So red-black trees, you've probably heard, have what we might call an isometry with B trees, meaning that they basically are the same thing. There's a one-to-one mapping for every LLRB. You can give me a valid corresponding B tree and vice versa, right? They're basically the same thing, just in slightly different forms. So I'm going to show you how to transform a B tree into an LLRB, and it's actually not that bad. So basically, here's all you have to do. So there are only really two types of nodes in a B tree, right? You have a node that either has one thing in it, or one thing in it, or a node that has two things in it, right? And it turns out all we have to do is transform these into a corresponding B tree. So let's say that we have a node in a B tree that has an element in it. Let's just say it has an element X. What we're going to do, if we want to turn this from the B tree representation to the LLRB representation, is we're just going to turn this into a single black node of our LLRB. And then if we have a two node, let's say we have an X and we have a Y, and we want to turn this into the corresponding LLRB, what we're going to do is we're going to draw something like this, where the X is a red child of the Y node. Okay. So what does this basically mean? Basically, one way you can think of red nodes is red nodes basically mean I belong to my parent's node, right? A red node symbolizes the left part of a two node in a B tree, right? And then a black node just represents a single node in this case. If that sounds confusing, let me transform this one into a LLRB, and then hopefully it'll make a little more sense. So all we have to do is apply these two rules over and over again on every single node. So let's start at the top. We have this 8 and this 14. Well, 8 and 14 is a two node. So we want to turn that into a left red child and a right black node. So that means that we're going to have 14 on top. And then it is going to have a red child to the left, which is going to be 8, right? So we just took this thing and we just basically put it in this form is all we had to do. Okay, and then let's keep going. Let's go do the second layer of the B tree. So we have this 4, 6 node, again, another two node. So we're going to have a 6 here. That 6 is going to have a red child, which is going to be 4. Why is it a black 6 and a red 4? Again, same thing, right? We're just basically memorizing these steps and doing them over and over again. Okay, so some other children we have. Next child is going to be this 12. Okay, so this is a little bit more complicated. So the 12 is going to be a black node, we know, because it's just a black node in the B tree, so it's going to turn into a black node in the LLRB. But the question is, where are we going to put it in our LLRB? Well, if you remember the fact that our LLRB is a binary search tree, there's actually only one place we can put it, right? And it's to the right of this 8, right? Because 12 is between 8 and 14. This is the only place we can put it, basically. And then next, we're going to put this 18 here. Same thing, there's only one place we can put it. We can put it right here, and it's going to be a lone black node just because it's a single node. Here's another thing to kind of realize. So notice here, we have this 8 node. We have this node with 8 and 14 in it, and it has 3 children, right? A left child, a middle child, and a right child. These 3 children do exist in the B tree, right? It's just they're here, here, and here, right? I hope that makes a little bit of sense. But if you think of it this way, this was originally one node, this was originally one node, and you can kind of start to see how we've just taken the 3 children and we've just kind of put this node on its side and connected them that way. I hope that makes sense. Okay, so that's the second layer of this tree. Now, the third layer of this tree, most of these are one nodes. So they're just going to be single black nodes that look like this. Right? Notice again, these nodes go left, middle, right, and look at how we've done them in the corresponding LLRB, left, middle, right of this 2-node. So then continuing to the left, now at the 12 node, it has a 10 and a 13 right here. These are also both single nodes, so they're going to end up being black nodes in our tree. We have a 10 right here. We have a 13 right here. And then we have a 15, and then we have a 20 and a 38. So 15 should be relatively straightforward. Again, it's just a black node. It's the left child of the 18 node here. So it's going to be the left child of the 18 node down here. The last one is a little bit trickier, but it is a 2-node, right? And how do we transform a 2-node? Well, with the 2-node, we always put the value to the left as a child of the value to the right and make it a red child. So that means that the way we have to build this is we have 38 here, and as a red child to the left, we have 20, right? Okay, that's basically how you do this thing. So I may have done this relatively quickly, and you might think, okay, sure, I understand that if it's a 2-node, I break it up into this way. If it's a 1-node, I break it into this way, but how again do we connect things? And just realize it's all right here in the B tree. So again, if you're looking at the children of a 1-node, right, you just put it to the left or right. For example, 12 has 10 to the left, it has 13 to the right. And the corresponding B tree we see right here, 12, 10 to the left, 13 to the right. If it has 3 children, like this node, right, the 8, 14 node, remember this represents a 2-node, and it has a left child, a middle child, and a right child. Hopefully you can see how they start to correspond. Great. And that's basically all you have to do to actually transform this into a valid LLRB. So this is what I meant earlier when I said that a red node basically means you belong to your parent's node, right? Notice that all of the 2 nodes we have, the left child is always the red node to the bottom of the right child. That's basically what it means. Okay, so that's how you do an LLRB. If you ever have trouble trying to figure out how to insert an item into an LLRB because there are a lot of rules and rotations are really hard to do on paper, one thing you might actually try to do is just go the opposite way, turn it into a B tree, and then do the operation of B tree, which I think is easier, then turn it back into an LLRB, and then you know how to do it. So again, you can just follow this process we did here, back around the other way, and turn this back into a B tree. So let's just do that for fun really quickly. So notice that all of these nodes here represent 2 nodes. So I'll just circle them like that. And then look what we have. We have 8, 14. It has 3 children. One of them is this 4-6 node. One is this 12 node. One is this 18 node. 4-6 node has 3 children. 3, 5, 7. 12 has 2 children. 10, 13. The 18 node has 2 children. One of them is the node, I just realized this is supposed to be 15, and one of them is the node 20, 38. Oh, I did write it right up there. Okay, it is 15. Good, I just messed it up the second time. Anyways, that's basically all you have to do. And that's how you transform it into an LLRB and how you can transform it back into a B tree. Final conceptual question here we will address is if a 2-3 tree has a depth h, meaning that there are 8 h edges, remember that depth refers to the number of edges. So if there's just a single node that has a depth 0 tree, what is the maximum number of comparisons done in the corresponding red-black tree to find whether a certain key is present in the tree? Okay. So we can basically look at the logic we use here to figure this out. Okay, so we want to find the deepest B tree we can make, or the deepest LLRB we can make with a corresponding B tree. B trees are always going to be shallower, or almost always going to be shallower than LLRBs. Why is that? Because notice that in B trees, you can put 2 things on kind of one level, whereas in an LLRB, those 2 things have to be put into separate levels, right? Notice that this B tree here is 5 deep, whereas this one is only 3 deep. Okay, so basically, you can imagine the worst case for a LLRB is when you have all 2 nodes, right? Because when you have all 2 nodes, that means that every B tree node has to be broken into 2 different layers, right? You can imagine I'm actually not going to draw one out because we get really tedious really quickly to draw it, but you can see right here, right? Imagine if this was a 2-node right here, actually. Like imagine that this was a 2, 3, then you would also have a red 2 down here. Something like that. So what you'll see is that for every edge in the B tree, for every node in the B tree, we're going to have 2 nodes in the LLRB in the worst case. So what we're going to end up with is basically double the amount of possible nodes we can have in the B tree. So notice here, this B tree has 3 different nodes in it, and it has 2 edges in it. This is asking about how many comparisons we need. We do comparisons at nodes, not edges, which means if we have H edges, H in this case is 2, we will have up to 3 nodes. We'll have H plus 1 nodes. And now realize that we have to double that because for every node in a B tree, we get 2 corresponding nodes in an LLRB. So we get this, which is just going to be 2H plus 1 nodes. This is the kind of conceptual question that we love to ask on exams. So please try to familiarize yourself a little bit with kind of the maximum and minimum ways to generate B trees and LLRBs. I hope this helps.